So in this video, we're going to be looking at phase 2 of the simplex method, and more specifically, we're going to determine the direction of unboundedness of this program. So here we have a program with an objective function and a couple of constraints. Now that it's in the form that we want, we will create a tableau. So in a tableau, we're going to have the non-basic variables, x1, x2, and our constants, along with here we have one, two different constraints. So we'll create some variables for those constraints. We can call them x3 and x4. And our objective function, we can just call that z. So our objective function is negative 5x1 plus 3x2 and 0. And x3, we have 2x1 minus 1x2 plus 4. And for x4, we will have negative 1. For x4, we will have 0 minus 1x2 plus 5. Okay, so now what we must look at is we have to determine what our pivot variable is going to be. So for that, we look at this bottom row, and the pivot variable can be any variable that is negative here. So in this case, the only negative is negative 5, and that corresponds to x1. So our pivot variable is going to be x1. And now we must determine what is our exchange or blocking variable. So it's either going to be x3 or x4. Okay, so since we determined x1 as our pivot variable, we must let x1 equal lambda, x2 equal 0. So let's see if x3 will give us an upper bound on lambda, since we have a lower bound of 0, but we must get an upper bound. So x3 is going to be equal to 2 lambda plus 4 greater than or equal to 0. x4 is going to be just 5 greater than or equal to 0. So if we take a look at x3, it doesn't seem like lambda will give us an upper bound, because lambda is greater than or equal to negative 2, but we already knew that. So therefore, we don't have a constraint on lambda. So lambda can actually increase to positive infinity, which means our objective function will go to negative infinity, which is not very helpful, and this is exactly the definition of unboundedness. And if we look at x4, well, x4, it's pretty obvious to see that it's not dependent on x1 or x2. So therefore, we wouldn't be able to do the Jordan exchange using x4 as a blocking variable. Therefore, the problem is unbounded, and the direction of unboundedness is x1, x2 equal to lambda and 0. So now let's visualize this direction of unboundedness by showing a geometric interpretation for this problem. So we don't need to worry about the objective function, but let's take a look at these constraints. And what we'll do is we're going to convert these constraints into the form y equals mx plus b, shown here. That way it becomes easier to graph them. So let's add some ticks here. All right, so our first constraint, x2 less than or equal to 5, will be right along here. And our second constraint, x2 less than or equal to 2x1 plus 4, we'll have to graph that. So x1, when x1 is 0, x2 is 4, 1, 2, 3, 4. Okay, and then our slope is 2 over 1. So we'll go up 2 over 1. So we have that little corner of that rectangle cut off. x2 less than or equal to 2x1 plus 4. Okay, and then we also do have the constraint that x1 is greater than 0, greater than or equal to 0, and x2 is greater than or equal to 0. So we're going to have this region here, not counting that little triangle there. So this is going to be our region of interest. And as you can see, x1 can in fact grow infinitely large to positive infinity. And so this is why we showed here that that's the direction of unboundedness.